Alright, welcome back everybody. In this video we are going to actually be working on solving optimization problems, tying it to section 5.11 from AP Calculus. We're almost at the end of Unit 5. Alright, so all this video is going to do is we are going to utilize over and over and over again the 6-step process that we introduced in section 5.10 to go ahead and solve some optimization problems. I have a feeling it's going to take me 2 videos to do all the problems that I have here, but we'll see. Alright, step 1, draw a picture. Right over here we have a picture of y equals the square root of x and the point 5, 0. I'm going to label one other point on this picture. I'm just going to label a point right here, which I'm going to call x, comma, the square root of x, because that's the point on the curve. All right, so what we're trying to do is we're trying to find the point that is closest. So we're looking for the distance between this point, 5, 0, and the point x, square root of x. So I'm going to establish, and this kind of is step 2, 3, and 4 all in one. We're writing the relationship between these two and putting them in terms of what we see in the picture and getting us to our distance equation that represents the distance between these two. I'm going to use the distance formula. Difference in my x coordinates plus the difference in my y coordinates. And simplifying this, we get d equals square root of x squared minus 10x plus 25 plus x, or d equals square root of x squared minus 9x plus 25. So there's a formula that represents the distance between the point 5, 0 and any point on the graph of y equals the square root of x. All right, so now we want to optimize this distance. This is the equation that we want to optimize. We're going to find the derivative and look for the critical points. So we take the derivative of this, that's 1 over 2 square root of x squared plus 9x minus 25. Oops, I flip-flopped my signs there. Whoa! Sorry about that. Who knew that trying to erase would cause my presentation software to crash? But it did. So go ahead and erase this and fix it now. Fix my signs. So we've got 1 over 2 times the square root of that, and then applying the chain rule times the quantity 2x minus 9. And so d prime is equal to 2x minus 9 over 2 square root of x squared minus 9x plus 25. The derivative is equal to 0 at x equals 9 halves, or 4.5. I do need to check and see if the derivative is ever undefined, but what's inside the radical here is never equal to 0, and so we don't have any critical points there. So there's our one lone critical point at d prime equals 0. I'm going to go ahead and make a sign chart to do my analysis here. And if I put 4.5 in there, you know, it might not be a terrible idea for me to figure out where this expression is undefined, but I feel like that's more work than I want to do, because I feel like this is, you know, I found this single critical point and I feel like I'm pretty happy with what's going to happen here. And then at 5, this is positive, and at 4, this is negative, and therefore the value of 4.5 produces a minimum, which is what we're looking for, a minimum. And so the closest point to 5, 0 on y equals the square root of x is 9 halves, square root of 9/2. And there's our answer to this optimization problem. And that point is like right about here. All right, example 2. Two towers are 30 feet apart. One is 12 feet high and the other is 28 feet high. There's a stake in the ground between the towers. The top of each tower has a wire tied to it that connects to the stake on the ground. Where should the stake be placed to use the least amount of wire? So step 1 here for me is going to be to draw a picture. Got these two towers that are 30 feet apart. One of the towers is 12 feet tall. One of the towers is 28 feet tall. They're joined by a wire that's going to hit somewhere down here and connect these. Both towers form a right angle with the ground, so we get a picture that looks like that. If I call this distance right here x, that means that this distance right here is 30 minus x. And then I can use Pythagorean theorem to label some other sides here. This side right here is the square root of x squared plus 12 squared. And this side right here is the square root of the quantity 30 minus x quantity squared plus 28 squared. Okay, and so those two sides, the orange side and the turquoise side, those are our wires. Okay, those are our wires. So that's what we want to minimize. So the next thing we're going to do is write our equation that models this. I'm going to call the length of wire capital W. And the one piece of wire is x squared plus 144. We simplify that. And the other piece of wire, if I simplify all this out and multiply it out, I end up with, let's see, okay, I've got 900 minus 60x plus x squared plus 784. And so simplifying that, we get x squared minus 60x plus 1684. All right, so there's our W value. We're going to go ahead and find the derivative of this. W prime is equal to x over the square root of x squared plus 144 plus x minus 30 over the square root of x squared minus 60x plus 1684. So I applied the chain rule and canceled all that stuff out in my mind. You know, this was 1 over 2 square root of x squared plus 144 times 2x. This was 1 over 2 times the square root of x squared minus 60x plus 1684 times 2x minus 60. And then we canceled the 2's from the denominator with what's in the numerator. And now we want to set that derivative equal to 0. And I'm going to go ahead and use my calculator to do this. I want to solve this equation. So I'm going to go ahead and graph this. X over the square root of x squared plus 144 plus quantity x minus 30 over square root of x squared minus 60x plus 1684. All right, there's our function. I'm going to go ahead and look at the graph of this and see if we can find a critical point. And we see the graph going here. It looks like it's creeping up on the x-axis. And it looks like it might have crossed. I'm going to go ahead and change my window up a little bit, change my y values out here, change my x value and extend that a little bit. And take a look at this graph and where it falls. And it looks like it's going to cross through there. And indeed it does. And so I'm going to go ahead and calculate this value. So let's see, we've got, we're looking for the 0. There's our lower bound and our upper bound. And we find out that that happens at x equals 9. And we can use this graph to help us make our sign chart here. We see that the derivative is below the axis to the left of 9 and above the axis to the right of 9, which means that when I make my sign chart, it's going to be negative to this side and positive to this side. So here's my sign chart for W prime. It's negative over there, positive over there, which verifies that this is a minimum since it's a relative minima. And therefore, the least amount of wire is used by placing the stake nine feet away from the 12-foot tower. All right. And it's 21 feet away from the taller tower, the 28-foot tower. All right, so we're going to call it quits there for today with this video. We'll come back in the next video and do a couple more examples of utilizing optimization concepts. And I'll see you then. Have a great rest of your day.